are we still missing? So I've said that intelligence is the efficiency with which you operationalize the past to face a constantly changing future. But of course, if the future you faced had really nothing in common with the past, no common ground with anything you've seen before, you could not make sense of it, no matter how intelligent you were. But here's the thing. Nothing is ever truly novel. The universe around you is made of many different things that are all similar to each other, like one tree is similar to another tree is also similar to a neuron, or electromagnetism is similar to hydrodynamics, is also similar to gravity. So we are surrounded by isomorphisms. I call this the kaleidoscope hypothesis. Our experience of the world seems to feature a never-ending novelty and complexity, but the number of unique atoms of meaning that you need to describe it is actually very small, and everything around you is a recombination of these atoms. And intelligence is the ability to mine your experience, to identify these atoms of meaning that can be reused across many different situations, across many different tasks. And this involves identifying invariance, structure, things that seem to be repeated, principles. And these building blocks, these atoms, are called abstractions. And whenever you encounter a new situation, you're going to make sense of it by recombining on the fly abstractions from your collection to create a brand new model that's adapted to the situation. So implementing intelligence is going to have two key parts. First, there's abstraction acquisition. You want to be able to efficiently extract reusable abstractions from your past experience, from a feed of data, for instance. And then there's on-the-fly recombination. You want to be able to efficiently select and recombine these building blocks into models that are fit for the current situation. And the emphasis on efficiency here is crucial. How intelligent you are is not just determined by whether you can do something, it's determined by how efficiently you can acquire good abstractions from repeated experience, how efficiently you can recombine them to navigate novelty. So if you need hundreds of thousands of hours to acquire a simple skill, you're not very intelligent. Or if you need to enumerate every single move on the chessboard to find the best move, you're not very intelligent. So intelligence is not just demonstrating high skill, it's really the efficiency with which you acquire and deploy these skills. It's both data efficiency and compute efficiency. And at this point, you start to see why simply making our AI models bigger and training them on more data didn't automatically lead to AGI. We were missing a couple of things. First, these models lacked the ability to do on-the-fly recombination. So at training time, they were learning a lot. They were acquiring many useful abstractions. But then at test time, they were completely static. You could only use them to fetch and apply a pre-recorded template. And that is a critical problem that test adaptation is addressing. TTA adds on-the-fly recombination capabilities to our AI. And that's a huge step forward that gets us much, much closer to AGI. That's not the only problem. Recombination is not the only thing missing. The other problem is that these models are still incredibly inefficient. If you take gradient descent, for instance, gradient descent requires vast amounts of data to distill simple abstractions, many orders of magnitude more data than what humans need, roughly 3 to 4 orders of magnitude more. And if you look at recombination efficiency, even the latest state-of-the-art CTA techniques, they still need thousands of dollars of compute to solve ARC1 at human level. And that doesn't even scale to ARC2. And the fundamental issue here is that deep learning models are missing compositional generalization. And that's the thing that ARC2 is trying to measure. And the reason why is that there's more than one kind of abstraction. And this is really important. I said that intelligence is about mining abstractions from data and then recombining them. There's really two kinds of abstraction. There's type 1 and type 2. They're pretty similar to each other. They mirror each other. So both are about comparing things, comparing instances, and merging individual instances into common templates by eliminating certain details